Hello, so this is section 10.3, and I started off with a quote from Monty Python, and now for something completely different. So, up to this point in our career, we've been dealing with what they call rectangular coordinates. And as we might learn, if you take linear algebra, coordinates are weights or addresses of vectors. And for us, in a coordinate system, basically, if someone says go over 1, 2, 3, 4, and up 1, we would say you're at 4, 1. But that's not the only way to do it. You don't have to just march over 4 and rise 1. There is also the polar coordinate system. And the polar coordinate system, for that same point, let's superimpose this. The polar coordinate system would say, I want you to, instead of going rectangularly, which is right and up, instead I want you to turn a certain angle, call it theta, and I want you to travel 4 units in that direction. And this ordered pair would be r comma theta, whatever that might be. So the polar coordinates are saying turn and fire, so to speak. Oh, and by the way, if r is negative, it says turn and fire in the opposite direction. So yes, we can have negatives as well. Let's explain that one. So in rectangular, where you have the x and y going on, and someone says, go over 1, 2, 3, but then go negative, that means go down 2, let's say, 3, and then negative 2. Okay, so y can be negative. We know that. If y is negative, you go below the axis. If y is positive, you go above. But in the world of polar, what would happen is if r is negative, it does the following. So there is an angle that points in this direction for sure, and you could not bother with a negative r value, but I'm just saying there's this possibility of also pointing in the opposite direction, which would be this angle theta, and then going backwards, so to speak. You would go backwards by going, I'm going to go negative r in that direction. So we are pointing in this direction here. We're going in that direction, but we're traveling backwards. So this r value here would be, or this ordered pair would be whatever negative r is and theta, okay? So yes, r being negative means go in the opposite direction. So a negative r value is defined to mean, or means, go in opposite direction. It's almost like you're playing a game, like these are the rules on how to play Catan or whatever, and away you go. So these are the rules for plotting points, actually. By this picture, you're able to see, if I put a point out here in space, call it x, y, okay. So you're going to travel x and you're going to travel y. We know from trigonometry there's an easy jump to this picture. This is a very common picture in trig and in geometry itself, okay? And there are relationships that are important to us. And the relationships that we see here, first of all, there's Pythagoras that says if you add x squared and y squared, you get r squared. Also, you can relate theta to y and x by saying y over x is really tangent of theta. If you continue with the SOHCAHTOA, if you go sine theta is equal to y over r, or cosine theta is equal to x over r, we get another pair of really helpful identities, and it says y is equal to r sine theta and x is equal to r cosine theta. So these guys, you're going to want to eventually, by doing the homework, they'll become memorized. Of course, everything comes from this picture in trigonometry. Okay, so that being said, a little more knowledge here. This, actually, I should say, I'm going to break this section up into, believe it or not, I think it's going to be 4 videos because there's so much going on in the introduction to this subject. Okay, there's a lot of graphing, and he even throws a little calculus at you. So the way it's going to go is once we get through the introduction here, we're going to go into circles and limicons, rose curves, and then finally slopes of tangents. So we're getting close, man, close to finishing this chapter once we get to here. Okay, so part of what they do is what we want to be able to do is to go back and forth between rectangular, which is where we were born, and now we are naturalized there, and then to polar, in which we are an alien or whatever, and we got to learn the ropes. Okay, so what we're used to is a point that, you know, could be something like, I don't know, let's pick on 4-1. Okay, if I want to write that in polar, then I'm going to use these identities to figure things out. What I notice is that, for instance, if I want r, I realize that r is really just the distance formula. It's going to be the square root of x squared plus y squared. It's the hypotenuse. So for this particular one, we've got 16 plus 1, so r is the square root of 17. Furthermore, I know that, for instance, if I want theta, I'll go with tan theta as y over x. So what we're getting is 1/4 there. So that tells us that theta itself is arctan of 1/4, whatever that ends up being in radian measure. When you state the point as a pair of polar coordinates, it's always r first and then theta. So for this particular guy, it's radical 17, and then I won't bother computing it, but oops, tan inverse of 1/4 would be the answer. Okay. In rectangular, there's only one way to write it. In polar, there's an infinite number of ways of writing an address in polar, and we'll get to that in a second. What I would rather do is maybe go the other direction. Say someone gives you something like, oh, I don't know, another example. So let's draw a little line here. Another example could be r is 3, and theta could make up something like 4 pi over 3, or it could be negative or whatever. Okay, this time we want to go the other direction. What's really handy in this case is, you know, x is equal to r cosine theta. So we're getting x, we're converting to rectangular. Okay, so we're getting x is 3 cosine of 4 pi over 3, which you can use a calculator or you can use your noodle. Let's see, 3, that's a 60-degree angle in that direction. So we're getting, it's equal to 3 times a negative 1/2. Okay, so we're getting x is negative 3 over 2. Likewise, y is 3 sine of 4 pi over 3. In that case, it's 3 times, in this case, it is a negative radical 3 over 2. And so y is equal to a negative 3 root 3 over 2. And thusly, our rectangular coordinate would be written as x and y. So negative 3 over 2 and negative 3 radical 2 over 2. There. So we've got going back and forth. And you can see with one example of each, I think you guys are going to be, you know, humming along with those exercises when you see them. Oh, I'm running out of room. What's next? Converting. Well, we did kind of convert right there to the other coordinate system. So what we did here is what we're going to do on the next page also. I think what I had in mind on this video is to show you the different ways of representing the same point, so I'm actually going a little bit backwards here. That's okay. Also, when you're converting, we're going to run into polar functions. So you could have a polar function. Okay. And so I'll give you one that's really simple. You ready? R is equal to 4. Okay. And the idea is somehow to convert over to rectangular. Okay. Well, here's how you do it. Which one do we use, George? You go up here. If I'm going to rectangular, I don't have but R. how can I write r in terms of x and y? Let's see. Oh, here you go. That one, right? Okay. So we could say that instead of r, we can say the square root of x squared plus y squared is 4. So therefore, x squared plus y squared is 16. And from your study in 10.5, you know that you have a circle with center 0, 0, the origin, and radius equal to 4, right? By converting. But you see how much simpler this is in polar? And that's a hint to the power of polar coordinates. Is that sometimes something that's awkward, say, in rectangular, makes much more sense in polar. R equals 4, really? Well, you don't know much about this yet, unless you listen to our Zoom meeting. You're a little bit better off. But basically, R is 4 means you've got, it's like taking a constant function rectangular. It just says your ordered pairs are of the form 4, 4, 4. I don't care, I don't care, I don't care. Whatever angle you want for theta, as long as r is 4. So you can point in the 0 direction and go out 4. You can point in the pi over 4 direction and go out 4. Pi over 2, whatever angle. And what are we scoping out here? Yeah, we're scoping out a circle centered at the origin with radius 4. Because all it's saying is theta can be anything. It can be any angle you want. And no matter what angle it is, as long as you go out 4 units, you're on the curve. And so, yeah, there's our first curve, by the way. And that's actually, I think, our next video when we start sketching curves. We'll talk about circles. And here's our first one. All right? Pretty cool. Okay, so let me backtrack a little. We've done a little bit of actually converting to the other coordinate system. So we've kind of done that, which is cool. I might think of something else to do by snagging a peek at the homework on page 666. Don't like saying that number. Anyway, so the polar coordinate system, though, is interesting because you know that the xy system, x just goes forever this way and y just kind of does its thing, whatever value you get. But in the sense of polar, if you take the independent variable theta just kind of goes in this direction. If it's positive, it can also go negative. But it just goes and goes and goes this way. This is its field of study. It just keeps rotating and rotating and rotating backwards, whatever theta value you want. So it's as if this thing here, up here, is wrapped around the pole, wrapped around the origin. And so you end up with a lot of graphs that just do whatever they might do. They might and repeat and things like that. Okay, so any point, okay, the point of this is that any point on the curve can be hit an infinite number of times if you let theta just go forever. Okay, and what that means to us is in this picture, let's say you have a polar coordinate of, say, making something up, 5, comma, and then pi over 4. Keep it simple. Okay. Well, we can map that, and that's the first thing you want to master is being able to map that. The first thing, I know it's backwards. I really don't like the order that they have here. I like theta first and then r, because that's how I think. I go, there's the angle, and now travel that far, right? But for some reason, it's this way. Anyway, you start in standard position, of course, and you go 45 degrees, or pi over 4. We know how to do this now, right? And then along this line, you're going to go, 1, 2, 3, 4, and 5, and plot a point there, and that's your point. Okay? But because theta is allowed to travel as much as you want it to, you can also have theta just what? Spin around a full 360 and land there. So another representation for this is 5 comma, let's see, that would be 9 pi over 4. And all I did was I did 1/4 plus 2 is 2 1/4. Did I do that wrong? 9 pi over 4. No, 2 1/4. Yeah, that's correct. 9 pi over 4. Okay. And you can spin around as many times as you want. So there's an infinite variety there. Now I want you to pay attention to this little demonstration. You can also go in the negative direction, in which case the angle in that case would be what, negative 7 pi over 4? And the distance still is 5. And you can spin negatively as many times as you want. So there are definitely, I'll write this out, there is an infinite number of ways to address, if you will, any point using polar coordinates. Surprise. Okay, surprise. We're still not done because remember that r can be negative too. R can be negative. So we could actually spin out in this direction and halt with an angle in that direction and then reverse our steps. So for example, this guy is, I can do it this way. I can say it is 5 pi over 4. But I can also call it what? Negative 3 pi over 4. And the r, once I'm in this direction, say this is 5 pi over 4, I'm pointing that direction, but instead I'm going to travel 1, 2, 3, 4, 5 in the opposite direction. And so in that case, I would put a negative 5, etc. Pretty interesting stuff. That's what's been invented for our amusement, if you will, actually for great use. I've seen it used in wonderful ways, but I haven't traveled that much. This stuff is here to stay, and of course I've taught Calc 3, and we've had to do cylindrical and spherical coordinates, and it's based upon our knowledge of polar first. Okay, so this is important for Calc 3 to get this digested, so to speak. So you're converting back and forth, you're changing functions into rectangular and back. I think back, yeah, you can do that too. There's all kinds of neat things. In our Zoom meeting, you'll see other examples I've done. And then you'll see things like, this is problem number 8 on page 666, number 8. It says sketch the region and what they give us is 0 less than or equal to r less than or equal to 2. If you stop there, that's interesting. But then they go pi less than or equal to theta less than or equal to 3 pi over 2. Okay, something like that. 3 pi over 2. All right. I know we're thinking rectangular still, and you have to kind of, okay, I got to get my mind off that. The world of polar, like I said, just spins around and around, you know, in either direction. So, and the world of, so it spins around. The world of rectangular just seems to unfurl left and right like a giant scroll, okay, but not so with polar, okay. So this is a fun game too because you have to kind of conceptualize differently, and that's why it's in the book. So here's the world. When you're in polar, you'll start to do this. Label the axes differently. Label them as you would in trigonometry, right? And so r is said to be going to be between 0. By the way, if r is equal to 0, you are at the origin. Okay, so 0, but then go out to 2. But theta can be anything. So remember that game where we did r is, well, we did something else, but in the class we did r is 2, and it creates this circle. But this says more than that. It says r is between 0 and 2. So that means he's anything in between, and you end up with this solid circle, okay, if that makes sense to you. But furthermore, they restricted us with theta. We're not allowed to spin from 0 to 2 pi and around and around. Instead, all we can do is have theta run from, say, pi, which is here, to 3 pi over 2, which is here. That's the only angle that we can do. So therefore, really, this region is this guy. And that's it. Okay? So sketching an introduction to the polar coordinates, this is what I'm doing in this first video. Play around with problems in section 10.3 all the way through to when we start sketching the curves. Then I want to guide you through the curves with 2 videos before we do tangents in the 4th video of this section. Okay, guys? And I think that's it for this one. Is there any surprises? No, that's it. Okay, we'll see you at the next video.